This is an example of a DC mesh solutions problem in Circuit Tutor on level 1. Let's go into that tutorial and click on an easy or level 1 problem. Okay, so here are the instructions if you want to review those. And in the solution game, we are given the KVL equations, so we don't have to write those. But in level 1, we do need to write the SOT variable equations. In this case, it's a SOT current. So let's do that. So we'll select SOT branch current, and then I0 is equal to, and we look for I0 is down here, so that has a single mesh current going through it, going opposite to its direction. So that's going to be I1, but it's going to be negative I1 since the arrow points the opposite of the direction of the mesh arrow. So that equation is correct, and now we've written all of the required equations for this circuit. So we'll click No More Equations. And now this is the new thing in the solutions tutorial, is that we're going to combine the coefficients in the KVL equations into a simplified standard form in preparation to solve them. And when we do so, we can multiply equations through by a constant if necessary, but we cannot, for example, add one equation to another equation to form a linear combination, or make any kind of substitutions in those equations in Circuit Tutor. So let's enter the first equation. So we see we have I1 times 9 and 6, so that adds up to a coefficient of 15 for I1. I2 does not appear in that equation, so that'll be 0. I3 appears here with a coefficient of minus 9, so we have negative 9 times I3. And then the constant term will bring the 8 volts over to the right-hand side, since that's the only constant term, and that'll of course give us a plus 8 on the right-hand side. Then for the second equation, we don't have any I1, so that'll be 0. I2 is multiplied by 4 and also by 6, so that adds to 10 I2. And then I3 here we have minus 6 I3. And then the constant will be the 7 volts from the voltage source that gets brought over to the right-hand side. So we added 7 to both sides. Then for the third equation, we do have an I1 actually. It has a coefficient of negative 9. And then for I2, we have a coefficient of negative 6, and that's it. So that'll be the negative 6. And then for I3, we have a coefficient of 6 plus 3 is 9, plus another 9 is going to be 18. So that'll be a coefficient of 18 I3. And then there is no constant term that doesn't multiply one of the currents in that equation, so the right-hand side will be 0. So that's the simplified equations in standard form. So now we'll check those. And those are correct. Now the next task is to take these simplified mesh equations and put them into a matrix form. So we actually can just click the button here to copy those coefficients, so we don't have to go through the tedium of retyping them. And again, the 15 multiplies the I1, 0 times I2, negative 9 times I3, that's equal to the 8. So that's the first equation, and then so forth on the, so this equation, for example, is the third row with a negative 9 times I1 minus 6 I2 plus 18 times I3, and then the right-hand side is 0. So that's just the matrix form. So we'll check that. And now the goal is to solve these equations, and of course our ultimate objective here is just to find I0, which requires knowledge of I1. Now we're going to use Gaussian elimination here, since we have only KVL equations. No obvious substitutions are possible, so we're going to solve this using a Gaussian elimination process, which is a way of doing a 3x3 system or a larger system. For 2x2, that would probably be overkill, but I mean, you could do it in principle, but let's do it with Gaussian elimination. Now your instructor may want to see your handwritten work here. If they do ask you to retain that, then you would need to keep that paper and turn it in if they so request. Okay, so now let's look at the algebra that would be involved. So what I've done here is simply copied this matrix equation over here and formed what's called an augmented matrix. So I have the matrix, the 3 by 3 matrix of coefficients here. I've simply copied, so 15, 0, minus 9, 0, 10, minus 6, negative 9, negative 6, 18, so forth, just copied from here. And then I've drawn a vertical line, and then I've added another column which consists of the constants. So this is known in linear algebra as an augmented matrix. And we're going to use an approach called Gaussian elimination with back substitution. And this is also known as reducing this matrix to row echelon form, or REF for short. So row echelon form is the form shown here at the bottom, which means basically that if we look at the left-hand portion, in other words, the original matrix of coefficients, we want the elements on the principal diagonal that goes from upper left to lower right, those should be non-zero. And everything above it can be non-zero, but the elements below the principal diagonal, which are these 3 elements, should all be zeros. If that's the case, these are all zeros, then we would have what's called the row echelon form of the matrix, and that's suitable then to solve very easily for each of the unknown currents in the problem. So how do we get from here down to here? Well, we're going to do what are called elementary row operations. And there's basically 3 types of operations that we're allowed to do. So the first one would be to interchange rows. So for example, I could swap row 1 and row 2. That corresponds to just writing the original equation in a different order. And clearly that will not affect the value of the solution variables, the I1, I2, I3. I don't need to do that here, but for example, if this coefficient here were a 0, then I would actually need to interchange this row with one that would make it non-zero. Usually I'd want to pick the row that has the largest absolute value in this element in order to minimize the round-off error in the calculation. That's called a pivoting operation because this first element is called a pivot. So I don't actually need to do that here because this is non-zero and it's already the largest value, so it just makes sense to leave that there. The second type of operation would be to multiply any row by a constant, which of course corresponds to multiplying the original equation through by a constant, which we know from elementary algebra is a valid operation to do on an equation. That won't change its solution at all. Now, we don't generally need to do that when doing Gaussian elimination, although that would be needed when you're doing what's called Gauss-Jordan elimination, which that's actually going a bit farther to where we would then make all of these elements on the diagonal equal to 1, and we'd also try to zero out the elements on the upper diagonal portion of the matrix. And if we have that, we have basically the matrix of coefficients is now the identity matrix, and that means we could just read off the values of the 3 variables from the right-hand side. So that's one approach to doing it, but it does require typically more calculations than this method. And so this method is a bit more efficient, which is why I'm choosing this as the method to show you here. So let's begin. And again, the goal here is to get to this row echelon form. So we work on a single column at a time. We start in the first column, and this is already non-zero, so we don't have to do any row interchanges. This one's already 0, so we don't have to do anything to row 2 or row 1. But row 3, this is non-zero, so that's what we have to change. So we're going to replace row 3 by row 3, subtract from it this coefficient divided by this one times row 1. So if we take negative 9 times 15 times row 1, that's going to make this first element in row 1 be negative 9. And then if we subtract that from this, clearly that will give us 0 as the coefficient of the I3, which is what we want to have. So we're going to take R3 minus this coefficient divided by this one, and that's of course equivalent to R3 plus 0.6 R1. And so now we carry out that operation. So we're not doing anything to rows 1 and 2 here because we don't need to. So we just copy those over as I've done here. And then for row 3, the negative 9 plus 0.6 times 15, we know that that gives us 0, so we don't really even need to calculate that. Here there's nothing to add, so we just copy the row 3 down. Negative 6 becomes negative 6. In this case, we do have something, so we take 0.6 times that, so that would be negative 5.4. Add that to 18, and 18 minus 5.4 gives us 12.6. And then here we have 8 times the 0.6, so that will give us 4.8. And so we add 4.8 to 0 and just get the 4.8 down here. So now we've basically got the first column in the proper form. And now we work from left to right doing Gaussian elimination. So we're going to now work on the second column and try to get that in the proper form. So the leading element is non-zero as we want, so we don't have to do any row interchanges, and it's also bigger than negative 6, so that's good in terms of minimizing round off. And so we're going to simply take row 3, and we're going to subtract from it this value, negative 6, divided by this value, 10, times row 2. And we're using row 2 here to minimize this rather than, well, we couldn't use row 1 in this case because there's a 0 here anyway. But if there were a non-zero element, we still wouldn't want to use that because that would then make this element become non-zero. And we want to keep this one as 0. So we're only going to work with the row 2, which has a 0 in the leading element. So that's how we avoid messing up the first column. So again, we're going to take row 3 minus this divided by this, so that'd be minus a negative 6 over 10. So that's equivalent to R3 plus 0.6 R2. So we're doing actually to row 3 what we did with R2 we did with R1 up here. So carrying that out, the first row of course is unchanged, the second row is unchanged, so we just copy those 2 rows down. And then here we're adding 0.6 times 10, so that's going to be 6 to negative 6 is 0. That was by design that we got 0 there. Then we take the 0.6 times negative 6. That'll of course give us negative 3.6. We add that to the 12.6. and that'll just give us 9. And then for the constant, we multiply the 7 in this row 2 by 0.6. That'll give us 4.2, so we add that to 4.8, and that also gives us 9. So now we have achieved the desired row echelon form where we have zeros below the leading element in each row, and all the lower diagonal elements are 0. So this allows us now to do back substitution. And the first thing I can observe is to find I3. So I start from the bottom now and work my way to the top, because the bottom equation obviously is the simplest one. And this just says 9I3 equals 9. So clearly, dividing by 9, that means I3 is equal to 1 amp. And I'm adding the unit here. Now we take that value of I3 and plug it back into the second row, which represents another equation. And that one is equivalent to saying 10I2, because remember this multiplies I2. And then I'll take the negative 6I3 and put that on the right-hand side. So I have plus 6 times I3, which is 1, plus the 7, which is the constant that was already on the right-hand side. And of course, that's just 6 plus 7 is 13. And then just divide through, and that's, of course, very easy to do. So I2 is just 13 over 10, or 1.3 amps. Finally, then I take the values of I2 and I3 and use those in the first row, or the first equation. And that becomes 15I1, and then there's no I2, and so it's the negative 9I3. I'll add that to both sides, or add 9I3 rather to both sides, and so I get 15I1 is equal to 9 times I3, which is just 1, plus the original constant of 8 in that equation, and so 9 plus 8, of course, is 17, and so then I1 is just 17/15, or 1.133 amperes. So now I've computed the values that I need. So now we'll go to the form in Circuit Tutor and enter those numbers, 1.133. And then I2 is 1.3. And I3 was 1. And where these aren't exact, I want to make sure I have at least 4 decimal places to make sure that these numbers are accurate so that we won't have a lot of round off error, and that's why I try to carry through enough digits here to be accurate. Okay, so we'll check that now, and those are correct. And now the next step, it tells us, is going to be to use the SOT variable equation I found earlier, which is very simple, just I naught is minus I1, to find the value of I naught, which was our objective. So I0 is simply the negative of the I1 value. Those values have been printed down here for us. So that's easy. That's negative 1.133. And I'll check that. And that is correct. And that completes the problem. So you do have the option of getting a detailed explanation of the KVL equations if you wish to have that.